Okay, let's unpack this fascinating announcement from IBM. We're going to dive into what it really means for the future of computing.
Yeah, it's pretty big news.
We've got the official IBM press release and also some great coverage from ICE Spectrum to guide us on this deep dive.
Good sources.
And the mission here really is to get to the heart of IBM's, well, pretty bold plan. They want to build the world's first large-scale, fault-tolerant quantum computer.
That's the key phrase, isn't it? Fault tolerant.
Exactly. And we need to understand why this is such a huge deal.
Right, because this isn't just, some vague prediction for the distant future. IBM's put out a concrete roadmap, specific milestones.
Leading to a system they're calling Starling.
Starling, yeah.
And the headline numbers are,
Yeah.
well, they're kind of mind-blowing. Starling is expected by 2029.
Which isn't actually that far away in this field.
Right. And it's being built at this new data center, Poughkeepsie, New York.
Mm-hmm.
The press release claims it'll perform 20,000 times more operations than today's quantum systems.
20,000 times. That's a serious jump.
And here's the kicker, the scale. It's almost impossible to really grasp. Representing its computational state, they say, would need the memory of more than a quintillion.
A quintillion. Wow. That's 10 to the power of 48.
Of the world's most powerful supercomputers.
It's just, it's a number that really forces you to think about the sheer complexity this machine is supposed to handle.
But it also immediately brings up the absolutely critical challenge.
The elephant in the room.
Exactly. Because as powerful as that sounds, quantum computers today are incredibly fragile. Error-prone.
Massively error-prone.
If you try to do anything significant, anything long-running, errors just creep in. Boom. Everything gets messed up.
Totally corrupted.
And that's why this idea, this fault tolerance, is the major hurdle. It's the thing standing between these experimental machines we have now and, well, actually practical quantum computing.
So if we're going to get what IBM's claiming, we have to start right there. Why are current quantum computers so limited for serious work?
Well, the core issue is the qubits themselves, right? The physical qubits. They're just inherently unstable.
Super unstable. They're incredibly sensitive to, the tiniest environmental changes.
Temperature fluctuations, vibrations, any stray electromagnetic noise.
Anything, any little thing can make them flip or lose that delicate quantum state they're supposed to hold.
It's like trying to, hold a really complex thought in a super noisy room. You get distracted, you forget bits.
That's a good analogy. And in a quantum calculation, you're not just holding one thought, right?
Right.
You're doing a sequence of operations involving lots of these qubits, and an error in just one qubit or even one operation, it can spread, cascade through the whole calculation.
And corrupt the whole thing.
Exactly. So for anything beyond really small, simple problems, the error rate on these physical qubits just makes useful computation, well, basically impossible.
Okay, so how do you fight that? How do you make something so fundamentally fragile, reliable enough to actually run complex algorithms?
So that's where quantum error correction comes in. And the key idea here is the logical qubit.
Logical qubit, okay.
So instead of trusting one dodgy, error-prone physical qubit to hold your quantum information, you distribute that single logical bit of information across a whole group, like a cluster of physical qubits.
Ah, okay. Spreading the risk, sort of.
Exactly. And these physical qubits, they're constantly interacting in a controlled way, which lets you detect and, crucially, correct errors.
Without actually destroying the underlying quantum information you care about.
Precisely. You're essentially building a more robust kind of synthetic qubit out of many unreliable ones.
Right. So the cluster, the group of physical qubits, it collectively acts like one much more stable logical qubit.
And it has a significantly lower error rate than any of the individual physical qubits that make it up.
Okay, that makes sense.
And the theory behind it, it tells us you can suppress these errors exponentially, the more physical qubits you add to the cluster.
The more stable the logical qubit becomes.
Right. And the more operations you can reliably perform with it.
Okay, that intuitively feels right. More redundancy, more stability.
Yeah.
But here's the snag, right? The really brutal challenge and why practical fault tolerance has been so hard to achieve.
Efficiency?
Efficiency, yeah. If you need a massive number of physical qubits just to build one stable logical qubit, then building a system with, say, hundreds or thousands of logical qubits, which is what you actually need for the powerful computations.
Well, then you need an absolutely astronomical number of physical qubits.
Right, which becomes an engineering nightmare.
Exactly. And this ratio, this physical to logical qubit ratio, that was the huge roadblock with the earlier error correction ideas, like the
Like
surface
surface code, yeah. I've heard of that.
IBM actually explored surface codes initially.
Yeah.
And they found you might need something like 1,000 physical qubits
Thousands.
just to create one logical qubit.
Wow. Okay.
And Jay Gambetta from IBM, he's quoted in this IE Spectrum article, he basically calls that ratio an engineering pipe dream.
Yeah, you can see why. Building a system with, say, 200 logical qubits, that would mean 200,000 physical qubits.
Which is just, yeah, not feasible. Not with current tech or even near future tech.
So the fundamental problem wasn't, can you correct errors? It was, can you do it efficiently?
Exactly. Can you get that physical to logical qubit ratio down, way down, to something manageable?
And that is where IBM says they've had this major breakthrough. They're claiming they've, quote, cracked the code on this problem.
Yeah, that's the headline claim.
So what is this core idea? What are they proposing instead?
Okay, so the heart of their new approach is based on something called quantum low-density parity check codes, or qLDPC codes.
qLDPC codes. Okay, how are they fundamentally different from, say, that surface code?
The key difference really is in how the qubits interact on the chip. Surface codes mostly rely on connecting only nearest neighbor qubits.
Okay, qubits talking only to the ones right next to them.
Right. Which is, like, maybe simpler from a fabrication standpoint building the chip, but it leads to that massive overhead, that 1,000 to 1 ratio we talked about. qLDPC codes, though, they're designed to work differently. They use non-local interaction.
Non-local, meaning qubits can connect to others further away on the chip.
Exactly. They can share information with qubits that aren't just their immediate neighbors.
Okay, and how does that make things more efficient? How does talking to distant qubits help?
Well, it lets you detect and correct errors across the whole grid of qubits more efficiently, using fewer qubits overall. Think of it maybe like this. With surface codes, you're doing lots of little local checks, tiny regions, and you need loads of these checks across tons of qubits to figure out what went wrong.
Right, lots of little checks.
With qLDPC, because qubits can interact over longer distances, a single check operation can potentially give you information about errors happening in more spread out locations all at once.
Okay, so you get more information per check, kind of.
Yeah. Sort of, yeah. It significantly reduces the number of physical qubits you need to encode and protect one logical qubit.
So instead of that 1,000 to 1 ratio, what are we talking about with qLDPC? What's the target?
IBM claims it drastically reduces the number needed by roughly a factor of 10.
A factor of 10, so like 90% less overhead.
About that, yeah. Matthias Steffen, who heads up IBM's quantum processor team, he estimates that with this method, maybe a few hundred physical qubits
A few hundred?
could potentially yield 10 logical qubits.
Okay, wait, so that's a ratio closer to maybe 30 to 1, 50 to 1, something like that?
Right.
Instead of 1,000 to 1?
Exactly. That kind of reduction suddenly makes the whole engineering challenge look, well, much more tractable. Possible, even.
Yeah, it is a massive difference.
Okay.
And this isn't just theory, right? They put out papers on this.
Right. They released 2 detailed technical papers alongside the announcement.
What do they cover?
Well, one focuses on the physical architecture. Like, how do you actually build a chip that allows those non-local interactions? They talk about new techniques, these things called configurable couplers.
Okay, the hardware side.
Yeah. And the other paper tackles the processing of all the error information, because you need to constantly be reading out data about errors from the physical qubits, decoding it in real time using classical computers, and then feeding correction instructions back into the quantum system fast.
Right. That sounds like a huge computing challenge in itself.
It is, and the paper describes their approach for doing that efficiently at scale, which is, another absolutely critical piece of this whole puzzle.
Okay, so they have the need for efficient fault tolerance because qubits are flaky.
Right.
They have there's a qLDPC code approach using non-local connections to boost efficiency.
Yep.
Now, let's get to the how. They've laid out this concrete multi-year modular roadmap to actually build Starling.
Yeah.
Walk us through the steps.
Yeah, the roadmap is pretty interesting because each step is designed to tackle specific engineering challenges needed for these scalable, error-corrected systems. It's sequential.
Okay, what's first?
First milestone, expected in 2025, is called IBM Quantum Loon.
Loon, like the bird.
Yeah.
Okay, what's Loon for?
Loon is specifically designed to test and validate those key architectural bits and pieces needed for qLDPC codes.
Ah. The non-local stuff.
Particularly, yeah, the C couplers. These are the actual mechanisms on the chip that let them connect qubits over those longer distances.
Gotcha. So Loon is about proving they can actually build the hardware foundation for qLDPC, making sure the connections work.
Exactly. Testing the essential connections.
Okay. Makes sense. And after Loon, what's next?
The next step is IBM Quantum Kookaburra. That's expected in 2026.
Kookaburra.
And this is slated to be IBM's first truly modular processor.
Modular, meaning?
I mean, it's designed as like a fundamental building block, a self-contained unit that combines quantum memory with the logic operations.
Okay, a single working unit.
Right. And the significance here is scaling. Building one single giant chip with thousands and thousands of qubits is incredibly difficult, maybe impossible right now.
Right, the engineering pipe dream problem again.
Exactly. So the modular approach means you can potentially link smaller, more manageable units together to build a bigger system. Kookaburra is that first basic module.
Ah, okay. So Kookaburra is the first Lego brick, essentially. How do they test linking the bricks together?
Well, that comes in 2027 with IBM Quantum Cockatoo.
Cockatoo, they like their bird names.
Seems so. Cockatoo is designed specifically to demonstrate that modular scaling. The plan is to successfully entangle two of those Kookaburra modules.
Okay, linking two chips together quantumly.
Yeah, using different kinds of couplers, which they call L couplers, designed specifically for these chip-to-chip links.
L for link, maybe?
Could be, and this proves the concept, right, that they can actually scale up by linking these independent quantum processing units together.
Like building a big supercomputer out of lots of smaller processor nodes today.
Exactly the same idea, just quantum. It avoids trying to build one impractically massive chip.
That modular idea really does seem key. Okay, so Loon tests the connections, Kookaburra is the module, Cockatoo links the modules, and all of this leads to Starling.
Precisely. Loon validates the qLDPC hardware. Kookaburra gives them the modular block. Cockatoo proves they can link the blocks. All necessary steps on the path to Starling.
Which is the culmination. Expected to be built by 2028 and then available on the cloud in 2029.
That's the plan.
And Starling's target specs again. 200 logical qubits.
Yep.
And 100 million quantum operations. That's the goal for practical fault tolerance.
That's the target for this phase, yeah. And, you know, their published roadmap even looks beyond that. They mention a follow-on system called BlueJ.
BlueJ, what are the specs for that?
Planned for 1 billion operations and 2,000 logical qubits.
Wow. Okay, so they definitely have a vision for continued scaling if this whole qLDPC and modular thing works out.
It shows the ambition, definitely.
It really sounds like they've charted a detailed course, but okay, even if they see this mainly as an engineering challenge now, not fundamental science, there are still significant hurdles, right, to actually hit these dates.
Oh, absolutely. Yeah. I mean, while IBM is presenting this as a concrete plan, it is still incredibly ambitious. And that IE Spectrum article, it includes some perspectives that, you know, temper the optimism a bit.
Like what?
For instance, Mark Horvath, he's an analyst at Gartner. He acknowledges the modular approach makes sense, but he calls it very complicated.
Complicated how?
And he suggests it might be further off than people think.
Why is that modular approach so complicated in quantum specifically? I mean, we link classical computer chips all the time.
Well, the complexity comes from needing to maintain those super fragile quantum states between the modules.
Ah, right. It's not just sending classical zeros and ones.
Exactly. You need to actually entangle qubits that are physically on different chips or transfer quantum information reliably without introducing new errors. Developing those reliable, low-loss L couplers, the chip-to-chip links, and all the control systems to manage computation across these distributed quantum processors, that's a really significant engineering feat.
Okay, so linking the chips reliably, that's a major task in itself. What other big technical challenges are still out there?
Well, improving the fundamental quality, the fidelity of the basic quantum operations.
Meaning making fewer errors on the gates.
Yeah. Reducing the error rate of the single qubit gates, and especially the 2 qubit gates. That's still crucial.
How much better do they need to get?
Matthias Steffen, the IBM guy, he points out that the error rates probably need to come down by another order of magnitude.
Factor of 10 better.
Yeah, from where they are now. For this whole error correction scheme to actually work effectively in practice, you need the underlying physical qubits to be good enough to start with, you know, for the codes to have a fighting chance.
An order of magnitude improvement on something that's already really hard. That sounds tough. What's a key bottleneck there? What limits that fidelity?
A huge factor is qubit coherence times.
Coherence times. How long a qubit can like hold its quantum state before it just poof.
Basically, yeah. Before it decoheres and errors become unavoidable, it's critical.
Where are they at with that now?
IBM's made progress. Their latest Heron chips, they have coherence times somewhere between 150 and 250 microseconds.
Microseconds, okay.
And they've apparently seen up to 2 milliseconds in some isolated test devices.
Milliseconds is much better.
It is, but maintaining that kind of coherence, especially when you scale up to complex multi-qubit systems and then trying to maintain it across different modules, that's a constant battle.
Right. Longer coherence just gives you more time to actually do calculations and error correction before the state falls apart.
Exactly. More time to play with.
Okay. And what about just the physical infrastructure, the stuff around the quantum chip?
Oh, yeah. There are still plenty of engineering challenges there, too. The cryogenic systems to keep things incredibly cold, the complex control electronics, the sheer density of wiring you need. Even with the reduced number of physical qubits compared to the old surface code ideas, it's still a lot.
But the new approach does help there a bit. Fewer physical qubits overall means less wiring, less cooling maybe.
It definitely helps. The modular approach and the efficiency of qLDPC should simplify some aspects of that support infrastructure by lowering the total physical qubit count needed. But it's still pushing the absolute boundaries of engineering.
Okay. So we've covered the fundamental problem, flaky qubits, IBM's proposed solution, qLDPC codes, and their modular roadmap, and the significant engineering hurdles still ahead, linking chips, improving fidelity, coherence times, infrastructure.
Yep, that's the landscape.
So let's bring it back. What does all this mean for you, the listener? Someone who wants to cut through the hype and really understand the state of play in quantum computing right now.
Well, I think this announcement is significant because it's a shift away from just vague predictions. IBM has actually published a detailed multi-year engineering plan.
Right, it's not just someday.
Exactly. It's a plan for building a system specifically designed to overcome that primary obstacle. Fault tolerance feels like a specific path,
Yeah.
with named milestones, aiming towards a potentially practical machine.
It means those potential applications we always hear about.
Drug discovery, materials science.
Yeah, revolutionizing drug discovery, designing totally new materials with amazing properties, tackling complex chemistry atom by atom, solving huge optimization problems that are just impossible today. Those could potentially move from just theoretical possibilities to maybe real-world capabilities within the next decade. If, and it's a big if.
A very big
If IBM can actually execute this plan.
It really represents a major move in this global race to build useful quantum computers. They're laying out a detailed engineering pathway to try and achieve fault tolerance. It's IBM putting a stake in the ground saying, look, this is how we think we can make quantum computing practical.
Okay, so pulling it all together.
Yeah.
IBM's unveiled this plan for Starling, a large-scale, fault-tolerant quantum computer aiming for 2029. The core strategy, using these qLDPC codes, which they claim drastically cut the physical qubit overhead needed for error correction, thanks to those non-local interactions. And they've laid out that modular roadmap. Loon in 2025, testing the hardware. Kookaburra in 2026 is the module. Cockatoo in 2027, linking modules, all leading to Starling by 2029.
That's the timeline they've put out there. And yeah, while there's still huge engineering challenges and fundamental improvements needed in qubit performance, this does feel like it moves the conversation from abstract science towards a concrete, though still incredibly challenging, engineering project with a clear timeline.
Okay, and here's a final thought to leave you with, circling back to that almost unbelievable number at the start, the quintillion supercomputers.
Yeah.
What kinds of problems, what scientific or technological breakthroughs have just remained completely out of reach, precisely because they require that kind of computational power? The ability to model complexity on a scale needing the memory of 10 to the power of 48 supercomputers.
Right. What becomes possible?
What entirely new frontiers of discovery, or maybe efficiency, might finally become accessible when or if systems like Starling, and maybe Blue Jay after it, actually become available. What does that future really look like for fields we rely on every day, like medicine or materials science or even AI? What change?